Hello everyone. In this lecture, I'll be talking about differentiability of a function for BSc first year student. So in this lecture, I'll be talking very few things. I'll give the definition and on important theorem, then give an example. So that is enough for the first year. So these all are based on the limits. So go and read and understand the definition, examples of limits, and then this will be easy. So let I equal to ab be an interval and f maps I to r is a function and c is a point, interior point of f. Then we say this f is differentiable at c if limit extends to c fx minus fc by x minus c exist. So if this exists means that number will be finite. This is not infinite. There may be the limit may be infinite. In that case, we will say that the infinite limit. But here, when we are saying exist, that means that it exists and that limit is finite. If the limit be L, then L is said to be derivative of f at c and denoted by f dash. See, by this definition, we can prove all those formulas of derivative which we have studied in class 11 or 12. So just this formula, like d dx of a x to the power n is equal to n into x to the power n minus 1 or d dx of sin x equal to cos x. All these theorems can be proved by this limit. So even I think you have proved in inter also by this definition. So that is limit. So here see, if c is not interior point, that's also okay for this, but for these two, the interior point is needed. So if the limit fx minus fc by x minus c exists and equal to L, then this is called right hand derivative of f at c, and it is denoted by r of f dash c. And if the left hand derivative of this function exists, then that is called left hand derivative. See, in the definition of continuity, we have seen instead of x, we have used c plus h. So here also we can do the same thing. Like this expression will be limit h tends to 0 f of c plus h minus fc by h. And if that limit also exists, that is called. This is nothing but same. Actually, what we will assume, the x minus c is h. That means x equal to c plus h. So as x tends to c, so x minus c will be tends to 0. That's nothing, not a big thing. So this is the definition. So we know the limit, so we can calculate whether it exists or not. If it exists, then we will call it differentiable. And this is also point property. Actually, we have to prove point by point. So now we'll go to an important theorem, that is, if a function is differentiable at a point c, then it is continuous at that point also. But the converse need not be true, may not be true. First we will prove if f is differentiable at c, then it is continuous. So let c belongs to ab, and as it is given that f is differentiable at c, so that limit must be exist. Limit extends to c fx minus fc, x minus c is L, and L obviously this will be finite number. In the definition also we have possesses a finite derivative. That means this L will be finite. We have to prove that f is continuous at c. So how do we prove? We prove that if limit extends to c fx equal to fc, then that is if c is continuous, f is continuous at c. So for that, just we have written fx minus fc. What we can do it? Right? Fx minus fc by x minus c into x minus c. So we are assuming x not equal to c. That's why we are able to divide by x minus c. Now we take the limit on both sides. So limit of this equal to limit of this. This is nothing but, so here in this form f into g. So limit of this into limit of this. So limit of this is what? 0. Actually limit will be, if we put that value, like if we put x equal to c in that function, if it is not of the form 0 by 0 or infinity by infinity, actually if this is finite, then that will be the limit. So it will be 0. So L is finite, L into 0 is 0. So finite is needed here, because if it is infinite, that is 0 into infinity, that is indeterminate form, actually that is not defined. So finite is needed here. So this is 0, that means limit extends to fx, x tends to c fx equal to fc, because this is independent of x, so there will be no limit. So this means f is continuous at c. Now the converse part is what? If f is continuous at c, does it imply that f is differentiable at c? The answer is no. Here is an example. Say fx is equal to mod of x. So this is x and this is minus x. For x greater than or equal to 0, x less than 0. So this is the definition of mod and defined in whole R. So we will check the continuity at 0 point. So continuity, it will be continuous at 0. So we can show it in two ways. Like we know that fx equal to x, that is the identity function is continuous on R. Also we have done a theorem which said that if f is continuous, then mod f is also continuous. So mod of fx, that is mod of x, is continuous, or directly you can prove also. So f is continuous at every point, so it is continuous at 0 also. So but it is not differentiable at 0. How do we calculate? Let us calculate first right hand derivative. So this is limit x tends to 0 plus fx minus f0 by x minus 0. This is x and this is 0. So x by x, this is 1. But what is the left hand derivative? This is fx minus f0 by x minus 0. This is minus x. Actually left hand means the value should come from this, because this is give the left hand value and this is give the right hand value. So minus x by x, it is minus 1. So these are not equal. So that limit does not exist. So it is not differentiable. Now this example is also very important as far as the exam is concerned. So see, so the function is given by fx equal to x square sin 1 by x plus x cos of 1 by x, x not equal to 0, and 0 if x equal to 0. So we have to test the continuity and differentiability of this function. So in the continuity, we have proved this kind of function is continuous and this kind separately it is continuous. So in the limit and continue, we have seen that if two functions f and g are continuous, so their sum is also continuous. So first we split into two functions, f and g. Now g and h. F is given, so we have taken g and h. G is this and h is this. See, g and h will be the same thing. G plus h will be the function of f. So we will test the continuity and differentiability of these two functions separately. For this function, it is continuous. Although we have proved it in the continuity chapter, here I have given also the proof. So gx minus g0 equal to x square sin 1 by x minus 0. This is this. This is this. This is less than or equal to 1. So this is continuous, and this is also continuous. H is also continuous at 0. We are checking at 0. So their sum is also continuous at 0. So absolutely fine. Now we will discuss the differentiability of first function. So limit x tends to 0, gx minus g0 by x minus 0, that is x square sin 1 by x minus 0 by x. X cancel. This is 0. So this limit is 0. We can how do we prove? This proof will go same as this. So here we will take gx minus 0, because we are proving the limit is 0. So we are not proving continuity, we are proving that is 0. So here it will be 0. So here the function whatever it is come, it's x sin 1 by x. So everything will be same. So here instead of x square it will come x, and that is less than delta equal to epsilon. so that is also continuous. Not continuous, that limit exists and that is 0. So since this exists and it is finite, so f is differentiable at 0. But what about h? So let's check. So hx minus h0 by x minus 0, this is this, this is this. In the limit chapter, we have proved that this is does not exist. So this limit does not exist. So h is not differentiable. If h is not differentiable, then their sum f is also not differentiable. Why? Because we know that limit of the sum of two function is sum of the limits. But here we are getting one function does not exist, so we cannot calculate their sum. So this is not differentiable. In fact, we can prove this function. Even x square, if it is x only, then this function are not differentiable at 0. But it is x square, x cube, x pi. Here also x square, x4. Actually, the power is greater than equal to 2, and then it is differentiable. Otherwise, it is not differentiable. So here I stop the lecture. So if you have doubt, so you can send me mail. And see, these limit, continuity and differentiability are very important for the student of mathematics. In the second year also these things are there, and in MSc also you will read somewhere, and in the competition exam also you will find problems from this chapter. So this is very important. Thank you again.